Hey guys, it's Mr. Gilbert coming to you with the first introductory lecture of the year. You can follow along the guided notes. We will not complete the guided notes today, so just make sure you note that. We will not get all the way finished with the guided notes today. We're just getting started with the beginning of them. We're going to look at kind of what is science and how do we do science today. So it should be a review for you. There may be some new terms, there may be some new parts to this compared to the past, but a lot of it should be a review. So we'll start with just defining what is science. Science is a system of knowledge based on facts and principles. Science is a system of knowledge based on facts and principles. So it's all the stuff we know based on all the stuff we have observed over the years, over thousands of years of science. Here are all the things that we have noted, we have taken in, and so all that knowledge compiled together is called science. There are two types of science. There are natural and social science. So social science, what is social science? That is interactions of people. That is in their world, as far as what we see in social studies class, right? What we see in economics and politics and history and things like that. That is social science. This class deals with natural science, right? The nature and what's going on in nature. So there are three main branches of natural science. Three main branches of natural science. They are physical science, that is your chemistry and physics, those things. Life science, which is also known as biology, and that is dealing with anything that's alive. And then earth space science. Now, there are some weird overlaps there. We can't just fit everything perfectly into a category. So, for instance, my major in college was biochemistry. So that's the chemistry, like the molecular level of things that are alive. Other things like, if we look at fossil records and things, you're dealing with earth plus things that were alive. So there's a lot of overlap there. But the way we normally break them down is physical science, biology or life science, and then earth and space. All right, so let's talk about how we do science. And if you look at your guided notes, and there's a several step section there. So if you're looking at the guided notes, they're numbered kind of weird, and that's based on an old quiz. That's where I pulled that diagram from for you guys to have for your guided notes. So don't pay any attention to the numbers in the guided notes, but you see a several step process there. Now what I want you to understand is that the scientific method isn't this perfect setup where every time you do the scientific method you have the exact same steps, or not every science teacher, professor, scientist sets them out the same way. So understand this is the way that I teach it, the way I've broken it down, but it's not always exactly the same. All right, so the first step there, and so if you're following along in the guided notes, the first step there says observe, where it says 14 in the box. This is make an observation. To notice something needs to be studied. To notice something that we need to look at. Hey, I wonder why that does that. And so there's a question or problem that's stated after that. And so, for instance, if we were looking at coronavirus, just as something that is obviously going on right now and very practical problem for us to look at. A lot of scientists are studying right now. We're making an observation. People are dying of this virus. How do I stop the virus, or how can I treat the virus? So this first step there is an observation. And give me 1 second. It's been a hot second since we were in. There we go. So the first step, haven't used this since the spring. So the first step is to make an observation. Hey, people are dying of this virus. It's just really just noticing something. It's a very basic observation. And after that observation, we come up with a problem or question. Now, maybe Miss Mead or Mr. Chapman can clarify for their classes, but for me, I take either of those terms. There's a problem, or there's a question or a problem. So that could be man, the coronavirus is really killing people, we need to stop it. Or the coronavirus, how do I stop it? Those are really kind of the same thing. One's just a statement, one's written in the form of a question. So problem or question. And then a lot of people jump into hypothesis next, but that, if you look at the diagram there, you know that's not the case for the way we have it written here. And the problem is a hypothesis we often define as an educated guess, and that is in your guided notes, and you can go and write that in if you want. Hypothesis is an educated guess, but the problem is we can't really make a hypothesis unless we're first educated. So I'm going to put the word research here, research, or collect data. You'll see some people put collect data or research. I need to become educated before I can make an educated guess. All right, then we get into that hypothesis. I need to make a hypothesis. Now we're going to spend a little bit of time this week on hypotheses. And here's the thing. There are generally three ways we write a hypothesis. We can write a hypothesis as an if-then. If this happens, then this. If I treat COVID with bleach, it will die. It will go away. It will break apart at the molecular level. So if I treat COVID with bleach, then it will die. And so that is an if-then hypothesis. There are also two other types of hypotheses. And in this class, because this is not a college-based science class, we're not going to spend a lot of time on the other two. But you have something called a null hypothesis and something called an alternate hypothesis. So I'm going to move my camera here for a second. So types of hypotheses. You have if-then, which we will spend time on. If-then. You have something called a null or an alternate. And those kind of go alternate. Those are three types, and we'll spend our time in this class mostly on this. If you do go into college science, you'll spend more time on these other two. So an if-then hypothesis is if this, then this. If we change this variable, then this other variable will change in this way. A null hypothesis always starts out, there is no significant difference in this if we change this. So it's kind of flipped. All right. So the then comes first and the if comes after, if you will. So there is no significant difference in the coronavirus if we treat it with bleach. And so it's kind of flipped from how we think of an if-then. And an alternate is the positive antithesis of that, if you will. And the reason we write it negative, and that sounds terrible, like why do we write if there's no change there, that's why we write the null hypothesis in a negative format. And you're like, well, why do we write it negative? Well, in most science, there's a couple things. We don't want to assume anything, and we'll get to bias in a minute. We don't want to assume anything. And a lot of science is based on not being successful. And that sounds weird, but a lot of it's based on failures. And so, you think of something that we've studied for years and years, trying to cure HIV, trying to cure cancer, things that scientists have failed at for decades. And none of them have been successful, you could say. Now, obviously, we found treatments, we found ways to help and things like that. But no one has cured those things. And so, you have the most brilliant minds in medicine studying those things, and it's fail. Now, is that wasted? Did we waste our time? No, we've learned, hey, this doesn't work, but it did help a little. So let's try the next thing. Hey, this didn't work, but it helped in this way. So let's go to the next thing. And so we fail, but we learn. We fail and we learn. And so if you think about it, we become more educated with each of those steps. And so you'll notice that some of those arrows come back in that scientific method, and that's what we're going to look at here in a second. But understand that most science is based on learning a little bit at a time. It's not like a giant discovery. Most scientists don't get big credit. Not all scientists are famous, right? Only the scientists who are finally successful who can reject their null hypothesis and accept the alternate are the ones that are famous. The guy who actually discovers the cure for HIV will be so famous, right? The girl who finds the cure for cancer will be so famous. But that doesn't mean all those other people are useless. They're building the way. They're building the groundwork. They're paving the way for those other scientists. So most science is based on failure and learning and progressing and learning and progressing and learning and progressing. So that's why we write in null hypotheses. For more basic and how we apply in the world for most of us in our daily lives, if this, then this, right, is going to be our standard hypothesis. So if then is what we'll stick with for this class. So after we do our hypothesis, we're going to experiment or test. I'll take either word for my class. We're going to experiment. So we're actually going to do the research. We're going to do the experiment, right? And then what? We're gonna collect observations, lots and lots of observations. We're going to collect observations, and we're going to talk more about observations. I think it's tomorrow. In the next couple of days, we're going to talk about types of observations. Let me look at my notes on the board here real quick. Yeah. So if you notice, there's more about observations down further on your page. I think it's Monday. We're going to talk more about observations, but we want to think critically. We want to observe critically, and that'll include sometimes that'll include numbers types of research, numbers types of observations, like, oh, that's 5 centimeters, or there were 3 milliliters, or whatever. And then sometimes that's descriptive. It turned blue. It is red. It is soft. It is whatever. And so we have those 2 different types of observations. Again, we'll get more into that later. So we collect our observations. And then after we collect our observations, we will come to some conclusion. Now, conclusion. Now, that is kind of the end, in the sense that we now have seen our experiment all the way through. We saw a problem, we came up with an idea and researched it, and we saw what happened, and okay, so we have some answer. This worked or this didn't work. Now, what you see there is you see 2 boxes coming off of there, and you're like, okay, well, what are these boxes? Right? So one of them goes back to experimenting. All right, so this top one on your diagram, this top one comes back to the experiment. Oh, so what is that? Okay, so if you will, this is if your experiment is a success, if it worked. So I'm writing the word success there. If your experiment worked, you want to go back and test it again. We never assume that it's going to work the first time, or maybe make slight modifications. And so we do research on some medicine for the coronavirus, and it seems to work in the rats, and that we've saved the rats' lives with it. And so now we're going to test it on humans. We're going to go back and experiment and do a little more research with that and continue trying it. The bottom one goes back to hypothesis. And like, well, what is that? All right. And so I'm going to write unsuccessful there. And what that is where, okay, so it's not a waste. Let's say I try some new coronavirus treatment or vaccine, and it doesn't work. And so we're a failure, right? Like I said, most science is based on failing. Most science is based on, hey, we're going to learn something and move on to the next thing. And so it's unsuccessful. We try it, we treat it with something, it doesn't work. Well, what do we become? Did we waste? No, we became more educated. We became more learned about this topic. And so now we can make a more educated guess. And so we come back and we come up with a new hypothesis. Well, that didn't work, but here's what we learned, is that it helped a little bit, or it helped at first, but then it didn't work. And so we can come up with a new educated guess. And so, like I said, laying groundwork. Most science is about learning a little bit more, learning a little bit more, learning a little bit more, and we come up with a new hypothesis. And maybe that next one works. Maybe that next one is the cure to coronavirus, or whatever the case may be. And so, that's kind of how this process works. We're going to, hopefully, there's a lab that we like to do for this class, that we don't know, what lab's going to look like when we get back. But I'm going to give you a quick example of this in this video to give you an idea. So what we do in this lab that we like to do with you guys is you get 3 seeds of a radish plant, 3 seeds, and you plant them in this cup. And so we're going to refer to this example several times over the next couple weeks. So you take a styrofoam cup and you put so many centimeters of soil in it, and you plant 3 seeds in a triangle in the cup. You bury another centimeter or so of soil on top. We'll get into the details more closely later. And then you water with 10 mLs a day, and you put it in the window. All right, and so that's our control. Again, we'll come back to the parts of an experiment later, but that's our control. We know what's going to happen. Mr. Gilbert, Miss Mead have done this lab 100 times, and so they know what's going to happen. It's the standard, right? Everybody does the same one. And so you are going to do some research. Okay, what can make this work better? And so you say, well, I think that more water is better. So I'm going to water it with 12 mLs instead of 10 mLs. I think I have an idea. I'm going to water it with 12 mLs. If the radishes are watered with 12 mLs of water instead of 10 mLs, then they will grow taller over the first 3 weeks of their lives. That's your hypothesis. If radish seeds are watered with 12 milliliters of water instead of 10 milliliters of water, then they will grow taller over the first 3 weeks of their lives. And so you write this hypothesis. Sounds great. You did research that said that plants need more water, and so you're all hyped about your hypothesis. And so you do your experiment. And so you start watering with 12 mLs a day instead of 10 mLs a day. And maybe the first week it grows faster. And you look at everybody else's 10 mL plants, you look at your control, and you're like, all right, I'm intelligent. Look at me, I'm a scientist. Look, Mom, I'm a biologist. And so you're excited. But over the course of 3 weeks, your plant grows fastest first. But over the second and third week, your plant kind of levels off and in the end becomes shorter than everybody else's. So you got a good head start, but everything fell apart. And so you're like, it didn't work. Well, what did you learn then? All right, so you come to a conclusion right here. You come to this conclusion that, hey, more water is not necessarily good. But what did you learn? Did you learn something? Yes. So you come down here, it's unsuccessful. It was unsuccessful. But what did you learn? Well, I learned that it actually helped at the beginning. It helped my plant grow faster to start, but maybe once the plant starts growing, too much water kind of floods that seedling. And so you change your hypothesis for the next time. Okay, if I water for 12 mLs for the first week, and then I decrease to 10 mLs for weeks 2 and 3. And so maybe for the initial growth of the plant into a seedling, maybe that takes more water, but once it starts growing, it needs less. And so you make a new hypothesis. If radish seeds are watered with 12 mLs instead of 10 over the first week of life, then they'll grow taller than the control plant. And so then you go back and do another experiment. And so it's about building. It's about building, learning more, learning more, learning more, learning more. And that's how most of science works. All right, so following along in your guided notes there, we already talked about hypothesis, and hypothesis being an educated guess. So we know some things, and we're going to make a guess based on those. Science leads us to theories and laws. So a scientific theory, pardon me for 1 second while I look at my notes on the board to see how far I'm supposed to go. So a theory and a law. So a scientific law, I have defined in your notes, is a summary of a natural event that is continually be proven by an experiment. I can do an experiment over and over again. And show, oh, that's true, that's true, that's true. You think of the law of gravity. And I can pick up this pin and let go of it and drop it and it falls. Look, gravity's true. Over and over again with an experiment, I can show it, I can show it, I can show it to be true. That is a scientific law. Now, if I went to space, maybe, and dropped this, it doesn't fall. And you're like, oh, gravity isn't true. Well, it was further from the Earth. I'm out in space. It's not two objects. There's not, maybe a gravity between this pin and the Earth at that point because they're too far away. All right, so gravity doesn't say things fall. What does gravity say? Gravity is the attractive force between two objects based on mass and distance. And those two objects, the Earth and that pin in that case, are too far apart. So gravity is still true. Gravity is always true. It's a law. I can prove it with experiments over and over again. A scientific theory is a summary of a natural event with evidence to suggest it's true, cannot be proven with experiments. But, sorry, I got interrupted. Scientific theory is a summary of natural events with evidence, but they can't be proven with experiments. There has to be some level of predictability, though. And that's a key word, predictability. And so there's evidence and there's predictability, but we can't prove it to be true. So let's take the idea of Pangea. So the idea of Pangea, the idea that there was a supercontinent on Earth at some point. Let me get rid of my... Oops, wrong button. Sorry. So the idea of Pangea is the idea that there was once a supercontinent, right? All the continents are once pushed together. And there's all this evidence to suggest Pangea is true, right? The edges of most of you have studied this at some point along the way in science class, but all the continents have edges that line up like a puzzle. Okay, well, that makes sense. Well, there's mountain ranges that line up. There's fossil records that line up. A guy named Alfred Wegener came up with the idea. And so there's all this evidence to suggest it's true. Now, why is it not a law then? If everything says it's true, why is it not a law? Well, here's the thing, is we can't go back and push it all together. We can't go back and recreate it and make it happen again. There's no way to do an experiment and show them re-separate. And so we continue calling it a theory. Now, it has to have some level of predictability. What does that mean? Well, that means, maybe this coast here. All right, we got the coast of the United States here is Maine and Florida, and then coming down into South America, and then, here we go. And then maybe whatever coast is here, the coast of Africa, we see some fossil here, and we see that fossil here, and we see that fossil here. It should be some level of predictability. So if we find these here, and this part of this puzzle connects there, we should find the same fossils. And indeed, with Pangea, with the idea of a supercontinent, we find evidence of that to be true. We can predict where we find something else on another continent, which is really cool. And so if you look at, the idea of Pangea as a supercontinent, it's not controversial really at all. Why? Well, pretty much everybody accepts it. Even everyone from all mainstream scientists to the Creation Museum and the Ark Encounter and those guys, people from all different parts of life, belief systems and education systems agree with this. And there's evidence to suggest it, and then there's predictability, and it all works together. Now, when it happened and how it happened, you might have some arguments on or discussion on, but the fact that it is not really debated among hardly anyone. And so that is a really good theory. It's a good theory to base this concept on. The summary of a natural event with evidence can't be proven with an experiment, but it has some level of predictability. So that's the difference in a law and a theory. A law I can show you over and over again with experiments, but a theory is a summary with evidence and predictability, but I can't do an experiment to show you this is true. All right. Here. Last little thing I want to get in here, I'll go ahead and look at bias and technology in your notes. Bias is a prejudice or inclination to perceive observations or results in a particular direction. Bias, B-I-A-S. And that is like basically, you want this to happen, so you're going to observe it in that way, and report it differently. Maybe that can be just outright cheating. That could be you're measuring your plants and you just kind of err on the high side because you want your results to be right. That's outright just cheating the data. It can be how you report your results. It can be how you see things, perceive things based on what you want to happen. And that can be anything from direct science to relaying of the information. So I know in a lot of classes we've shown the documentary Blackfish to demonstrate this. Blackfish is a good documentary in a lot of ways, but Blackfish really is an anti-SeaWorld documentary. And what they don't tell you is there's a lot of information about, look at how bad the whales are being treated and that kind of thing. But what Blackfish doesn't tell you is most of the data they use is over 20 years old. And so SeaWorld comes out with a rebuttal of like, that's not what we do. We used to do that and we're sorry for that, but it's been decades since we've caught whales in that way and that sort of thing. And so the Blackfish documentary is really outdated. The people that are in the documentary were fired from SeaWorld for doing their jobs incorrectly and things like that. And so the documentary is really biased, to use that word, B-I-A-S, biased. They've presented information incorrectly to try to sway you. It's propaganda. And so we got to be careful of that in science. We got to be careful when we're reading stuff from other people, like, is there bias in this? And then we have to be careful when we're presenting information, when we're measuring, when we're doing the observations, when we're giving off information, like, make sure that we're not using bias. And the last thing we see there on the notes, we'll go 2 more words here. Technology. Technology is applied science to benefit humans. It's taking the science and how to make this work. So, and maybe we find some cure for some vaccine. We discover a vaccine for COVID, and so we have this vaccine. So now putting it into play, like taking it and mass producing it, finding a way to give it to people, what's the right age, and how are we going to give it to them, as in a shot or as a nasal spray, or what's this vaccine look like? That's technology. It's taking the science that we've learned and making it benefit the people. That's technology. And then the last thing we see there is a blank, used to represent an idea or object unable to be observed directly. That's model. We use modeling to observe things for a few different reasons. So we come up with an idea, or we have something that we've learned, or we need to present it to people, and there's, how do I present this information? Well, why do we use a model? Well, sometimes we use a model because something's too little to be observed directly. Maybe we're looking at chemicals, and so we have little models, little manipulatives, where we can build models, and you make a little water molecule, and you can show it to your teacher or your friend when you're studying. We can't build water with the atoms. It's too little. We can't see it. And so you got to have a model, something to demonstrate that. The next reason we do is because something is too big to be observed directly. So maybe we want to see what something looks like in space. What does an eclipse actually look like? Well, that doesn't happen very often. It's too big, and there's not, it's not, the timing's not right. And so we use a model to show how the moon, sun, and earth line up to show an eclipse. All right, so something's too little, something's too big, or something's poorly timed. That doesn't happen for another 200 years in space. We can't see it again. So too big, too little, wrong time, something that's too expensive. And so like we can't just practice this. So if you take guys who are working on flying a space shuttle, for instance, we can't just send them out to practice. Those are millions and millions of dollars. You can't just, hey, here's a spare space shuttle, go practice flying. So what do? We make a simulator. And so they practice in a simulator instead of taking the old shuttle out and driving it around. So those are all different reasons we model something. Again, too big, too little, wrong time, too expensive. Those are things that we model. So we can't observe it directly, and so we want to see it or use it or observe it in a different fashion. All right. So that's what we're going to start with our notes today. We're going to have a separate set of notes on observations, quantitative and qualitative observations, and variables. So you'll see something separate coming over those in the next few days. All right.